What is signal to noise ratio analysis in Taguchi method? How to quantify the signal to noise ratio values for our conducted experiments, and what are all the inferences can be arrived out from the SN ratio analysis. Let us discuss in this video. In our research work, if we perform any experimental analysis, the main things will be concentrated on identifying the significant independent variables of the process. This is the foremost thing. Independent variables are nothing but the input parameters of a process which you are going to set for performing the experiments. Okay. Second thing is analyzing the range of the independent variables we can have for conducting the analysis. Then the next important thing is considering the independent variables at different levels within the range. Next, we need to fix the dependent variables we want to measure or record and analyze. Okay. Next thing is DOE. Based on the number of factors and the number of levels, we have to plan for the design of experiments in this stage. Then by setting the independent variables at the required levels, by conducting the desired experiment, the required output responses can be measured or recorded, followed by the interpretation of results will be done. Okay. Independent and dependent variables. Independent variables of a process are not dependent on any other factors in the process. So only they are called as independent variables. Okay. So in a process, normally independent factors are the process parameters, are simply input parameters of a process. Okay, so simply the input parameters of a process are called as independent factors or independent variables because they are not dependent on any other factors of the process. Okay. On the other hand, based on the levels of the independent variables we have set, the output responses of the process will vary. So it is obvious that the output responses of a process depend on the input process parameter settings. Therefore, the output responses of a process are termed to be the dependent variables. Okay. So normally the dependent variables or dependent factors are referred to be the output responses of a process. Okay. For example, in case of making coffee, the amount of coffee powder to be added, the amount of sugar to be added, and the amount of milk to be added are the independent variables. Okay. And the taste and color of the prepared coffee are the dependent variables as they are depending on the amount of coffee powder, sugar and milk added. Okay. Second example, in case of turning operation in a CNC lathe, spindle speed, feed rate and depth of cut are the independent variables, and material removal rate and surface roughness are the dependent variables. They will be the output responses of the turning process. Okay. Considering one more example, in case of a TIG welding process parameter optimization analysis, few significant independent variables are welding current, weld speed and shielding gas flow rate. So these are the input factors for the analysis. And the tensile strength and hardness of the welded specimens will be considered as the dependent variables of the process. While conducting experiments, it is not sure that every time we can get the accurate and precise results. Okay. During the conduct of experiments, some of the factors can be controlled. They are the input factors. Okay. They are simply called as controllable factors. Okay. Getting error-free results while conducting an experiment is influenced by many factors. For example, weather conditions, part-to-part minute variations while testing materials, unwanted voltage fluctuations while performing a welding process, etc. etc. Okay, these factors are called as noise factors, which are otherwise known to be the uncontrollable factors. Okay. So noise factors are the factors that are either uncontrollable or difficult to control but cause variability in the process outputs. Okay. So in Taguchi method, the optimal parameter setting is identified as the input parameter combination which provides the desirable level of responses with a minimal effect of noise factors. Okay. For that purpose only, signal to noise ratio, that is SN ratio values are calculated in Taguchi method. Okay. How to consider the effect of these noise factors in the result of an experiment? For that, for testing a particular input parameters combination, more than one trial has to be performed. In a particular combination of input factor setting, in all the trials, if the deviation in the results is minimum, then we can say that that experiment has been conducted in a controlled environment with a minimal influence of the uncontrollable factors, that is noise factors. Okay. In signal to noise ratio analysis, signal means the mean value of the output values. Okay. The mean value for the output values for different trials of same input condition. Okay. And noise means the standard deviation between the results obtained from the different trials. Okay. Normally, in SN ratio analysis, three criteria are considered. The first one is called as larger the better criterion. Okay. In some experimental analysis, some output responses are desirable at their higher levels. For example, in case of testing the properties of materials, if the tested material has higher tensile strength, then that condition is desirable. Okay. So for such cases, larger the better criterion should be used. The formula for this criterion is SN ratio is equal to minus 10 log 1 by n summation I is equal to 1 to n 1 by yi square. Okay. Here this n is the number of trials we have carried out, and this yi is the output response value obtained in each trial. Okay. The second criterion is smaller the better criterion. In case of machining operation, surface roughness of the machined components should be minimum. For such cases, smaller the better criterion should be used. The formula is SN ratio is equal to minus 10 log of 1 by n summation I is equal to 1 to n yi square. Okay. The third criterion is nominal the better criterion for the factors which are desirable at nominal level. For example, hardness of the newly prepared composite materials. This criterion is used. Okay. The formula for nominal the better criterion is SN ratio is equal to 10 log y bar square divided by sigma square. Okay. Here y bar is the mean value of the obtained output responses for different trials. Sigma is the standard deviation. Okay. For case study 1, I am considering a TIG welding process parameter optimization work on aluminum alloy 6061. Here the input variables weld current, shielding gas flow rate and double V-groove angle are considered at 3 different levels within the possible range. Okay. With the help of Minitab software, we can generate the Taguchi's L9 orthogonal array table for this case. Okay. For that, we need to click Statistical, DOE, Taguchi, Create Taguchi Design. Okay. 3-level design. We are considering 3 factors. Display available design. For 3-level 3 factors, select L9 orthogonal array design. For fractional factorial, the available design is L9, and the full factorial design, the available design is L27 orthogonal array design. Select L9. Factors, weld current in amps. The considered levels are 150, 170 and 190. The second considered factor is shield gas flow rate in LPM. The considered levels are 6, 8 and 10. The third factor considered is double V-groove angle. Unit is degree. The considered levels are 30, 40 and 45. Okay. This is the Taguchi's L9 orthogonal array design. For each input parameters combination, 3 welded specimens have been prepared, and for all ultimate tensile strength values have been calculated using universal testing machine. The results are tabulated here for the trials 1, 2 and 3. The mean value of the ultimate tensile strength can be calculated as is equal to average of these 3 Here, the output response ultimate tensile strength of the welded specimen is desirable at its highest level. Okay, so larger the better criterion is used. By applying the SN ratio formula for larger the better criterion, log of 1 by n. Okay, here the number of trials have been taken as 3, so 1 by 3 into 1 by y1 square plus 1 by y2 square plus 1 by y3 square. Okay. So the SN ratio value for all the 9 experimental combinations can be calculated like this. Okay. Now, by ranking the input factor combination based on the largest value of SN ratio, this is the maximum value of SN ratio. So we can rank experiment 9 as 1, and the second largest value is 42.48. So we can rank experiment 3 as 2, then this is rank 3, rank 4, rank 5, rank 6, rank 7, rank 8 and this is rank 9. Okay. And by ranking based on the mean value of the ultimate tensile strength, the highest mean ultimate tensile strength value has been obtained with the 9th experimental combination. So we can rank experiment 9 based on the mean ultimate tensile strength value as 1. The second largest value is 133, so this is rank 2. Then 126.3, rank 3, 123.1, rank 4, 120.9, rank 5, 111, rank 6, 105.6, rank 7, 104.7, rank 8 and 99.3 megapascal, rank 9. Okay. Here we can notice that the ranks in both the cases seem to be similar. That implies the deviation in the results is uniform throughout the experimentations. Okay. Remember one thing, whether the output response is larger the better, smaller the better, or nominal the better, after calculating the SN ratio value, the optimal combination of input factors corresponds to the largest SN ratio value. Okay, so in this case, experiment 9 is ranked as 1. Therefore, it can be concluded that this input factor combination yields maximum ultimate tensile strength with the minimal deviation. Okay, without knowing the formula for SN ratio, we can perform this analysis simply using Minitab software. Okay, for that, here we have to go to Stat DOE Taguchi, define custom Taguchi design. Here we have to select the factors we are going to consider. Weld current, by double clicking the factors we can choose the factors. Second factor, shielding gas flow rate, and the third factor okay. Now we have to manually type the output responses for ultimate tensile strength for the 3 trials. Okay, ultimate tensile strength in megapascal, trial 1, ultimate tensile strength in megapascal, trial 2, then ultimate tensile strength in megapascal, trial 3. Okay, already we have the ultimate tensile strength values for the 3 trials for all the 9 experimental combinations. Copy them and paste here. Go to Stat DOE Taguchi and analyze Taguchi design. The response data, select UTS trial 1, UTS trial 2 and UTS trial 3. Click graphs, click signal to noise ratio and means. Okay. Analysis, signal to noise ratio and means tab have to be selected. Terms, the correlation terms will be mentioned here. Options, here the ultimate tensile strength value is considered under larger is better criterion. Okay. Storage, select signal to noise ratio and means. Okay. Click OK. So these are called as main effect plots. The interpretations can be taken out from these graphs will be discussed in the upcoming lecture video. So these are the calculated signal to noise ratio for the larger is better criterion, and this is the mean value of the 3 trials for each experimental combination. So from these values we can rank the experimental combinations, thereby we can identify the optimal input parameter combinations directly using Minitab software without knowing the formula for each criterion of signal to noise ratio. Okay. Next, for case study 2, I am considering a turning process parameter optimization work. Here the input variables cutting speed, feed rate and depth of cut are considered at 3 different levels within the possible range. Okay, for that select Stat DOE Taguchi, create Taguchi design, 3 level design, 3 factors, display available design. For 3 level 3 factors, select L9 orthogonal array design. Factors, the first factor considered is cutting speed in meter per minute at 3 different levels, 200, 400 and 600. Then the second factor considered is feed rate in millimeter per revolution at 3 different levels, 0.1, 0.125, 0.15. Okay. Then the third factor considered is depth of cut in millimeter at 3 different levels, 0.1, 0.2 and 0.3. Okay. So this is the Taguchi's L9 orthogonal array design for the considered case. For each input parameter combination, the surface roughness value has been measured on 3 different locations of the machined component using surface roughness tester. The results are tabulated here for the trials 1, 2 and 3. The mean value of the surface roughness value can be calculated as is equal to average of these 3, and the mean surface roughness value for all the 9 experimental combination can be calculated. Here the surface roughness value, this output response is desirable at its lowest level. Okay, if a machine component has lowest surface roughness value, then that is desirable for us. Okay, so smaller the better criterion is used for the case of surface roughness. By applying the SN ratio formula for smaller the better criterion is equal to minus 10 into log of 1 by n, here n is 3 trials have been considered, into, for smaller the better criterion, the formula is y1 square plus y2 square plus y3 square. Okay, so for all the 9 experimental combinations, the signal to noise ratio value can be calculated under smaller the better criterion. Now by ranking the input factor combination based on the largest value of SN ratio. Again, I am reminding that the factors may be of larger the better criterion or of smaller the better criterion, but after calculating the SN ratio value using any one of the criterion, then the largest SN ratio value will be corresponding to the optimal input factor combination. Okay, even though here the surface roughness value is desirable at its lowest value, the largest SN ratio value will be representing the input parameter combination yielding lowest surface roughness. Okay, so now we can rank the input factor combination based on the largest value of SN ratio. This is rank 1, 16.46, followed by 12.759, rank 2, 12.74, rank 3, 12.39, rank 4, 11.69, rank 5, 11.36, rank 6, 8.85, rank 7, 5.67, rank 8, and 1.00, rank 9. Okay, but by ranking based on the mean value of the surface roughness values, the lowest mean value of surface roughness is representing the optimal input parameter combination. So the combination of input parameters yielding the surface roughness value of 0.15 will be considered to be rank 1. Okay, the next lowest value of surface roughness is 0.23. So experiment number 9 and experiment number 5 both are having the same value 0.23. So both of the experimental combinations can be ranked to be rank 2. Okay, so next 0.24, so rank 3. Next 0.26, so rank 4. Next 0.27, so rank 5. Next 0.36, so rank 6, next 0.52, rank 7, next 0.89, so rank 8. Okay, so from the results we can note that even though the average surface roughness value in the experimental combinations 5 and 9 are same, considering the deviation in the results of trial, the deviation in the results of experiment number 9 is found to be lesser in comparison to that of experiment number 5. Therefore, experiment number 9 has been ranked as 2 and experiment number 5 has been ranked as 3. Okay? A good experimental combination is a one which offers the desirable level of output responses with the minimized effects of noise factors. Okay, that is with a minimal deviation in the results. Hence, in the present analysis, experiment 8 can be considered to be the optimal input parameter combination yielding minimal surface roughness on the machined component's surface. Okay. With the help of Minitab software, how this analysis can be simply performed, let us discuss. First, we need to manually feed the obtained surface roughness data for the 3 trials Surface roughness for trial 1, surface roughness for trial 2, surface roughness for trial 3. We can copy the required output values here and paste them here. Next, go to Stat, DOE, Taguchi, define custom Taguchi design. Here, select the input factors, cutting speed, feed rate and depth of cut. Then click OK. Next, go to Stat, DOE, Taguchi, analyze Taguchi design. Select the response data available for the 3 trials. Surface roughness trial 1, surface roughness for trial 2 and surface roughness for trial 3. Click graphs. Select signal to noise ratio and means. Click OK. Then click analysis. Here also select signal to noise ratios and means. Click OK. Next, terms. Click OK. Next, in options, select smaller is better criterion because here surface roughness is desirable at its smallest value. Next, click storage. Select signal to noise ratios and means. Click OK. These are the main effect plots for the SN ratio and mean values. These are the signal to noise ratio values of the uptime surface roughness values, and these are the mean values. From these data, we can rank the experimental input factor combination yielding optimal output response.